So the next talk will start now. Sorry for the technical delays. So this talk is given by Professor Victor Mukherjee from IISER Berhampore. As I already told, he did his PhD from IIT Kanpur, and then he was doctoral researcher in France, Italy, and Israel, Weizmann Institute. And since 2008, November, he is in IISER Berhampore. So please, you may start now.
Okay. So thank you. Thank you for the invitation and the introduction. So I will talk about stabilizing time crystals to non-Markovian dynamics. Sorry. Yeah. Okay. So it is done with my PhD student Bondita and my postdoc, ex-postdoc Naufal, who is now in Singapore, and my current postdoc Rahul. It is based on these two papers mainly. One was published last year, and the next one we are now working on it. So the first is I will talk about what time crystals and what is the motivation behind my talk, or what is the main question that we try to answer. And then I will talk about discrete time crystals, both in this dissipative discrete time crystals in the Markovian dynamics regime and non-Markovian regime. And then I will talk about continuous crystals, and finally I will conclude. So time crystals are whenever we have some broken symmetry in space. So now there is in this phase there is a long range order in both space and time, and so it is like some periodicity in some observable. We find some periodicity. So of course there can be several, like a very trivial periodicity, like if we just apply a pulse, the system will show a periodicity. But we are talking about something here in which this periodicity has, in the sense that even if the pulse has lot of error in it, still the inter-body interactions in a many-body system should be able to stabilize this phase. So that is why it is called a non-equilibrium phase in matter, in the sense that these systems are out of equilibrium, and this symmetry breaking is in time as well as in space. But this time crystal phase can be fragile in the presence of strong dissipation. That is, if there is a lot of heat, and then it can destroy the phase. So the main motivation is how to make time crystals robust against dissipation. Just as an example, say we have this spin chain. So they can be interacting with each other. There can be disorder in the spin chain or long range order in the spin chain. And say there is some pulse is applied, periodic pulse. And now if there is some, say, small dissipation or small kind of a error in the periodic pulse, and say if there is the spins are not interacting among themselves, then what will happen is that initially they might start showing a periodicity, but then they will quickly die out because of the errors in the pulse. But if we turn on interaction between the spins, then in some regimes, it is seen that it becomes a robust periodic behavior in time, even if there are some errors in this initial pulse. And this behavior in time, it causes this long range order, both in space, that is very far away spins are they are correlated, and also in time. So first I'll talk about discrete time crystals. So in discrete time crystals, this ordering in space and time is formed by some time-dependent Hamiltonian. So some pulse, like say some sigma x is applied periodically. And then some observable OT shows fixed oscillations with a period nt without fine-tuned Hamiltonian parameters. Now this n is some, say, positive integer. So here comes this time translational symmetry breaking. That is, even though the periodicity pulse is t periodic, the system chooses a one particular value of n, so that the order parameter or the observable shows a periodicity with time nt. So this is like a discrete time symmetry breaking. And without fine-tuned Hamiltonian parameters means like even if it is not exactly periodic or there is some small error, it still shows this periodicity, which would not have been there in absence of say interbody interactions or some kind of a stabilizing thing. And this is a many body system phenomena. It is not available in few body single systems. And this time crystal phase has to persist for long time. That is, it should go to till infinitely long time in the thermodynamic limit. I mean, which just shows that it is not a transient time phenomena. It should be a very stable phase. And as I said, the long range order is both in space and time. Here I and J are the spin indices, say lattice indices. And it has also been seen in the last few years in different systems experimentally. For example, in ion trap systems, they could have some disorder in the system, and the disorder, what it did was caused localization. And this localization, yes.
Okay, there is a question.
Yes, please.
Hello. Question. So, in your previous slide, so this n can be input, right? It can be even non-integer.
Sorry, could you please repeat?
The periodicity that you're talking about, n, this n could be
Yes.
non-integer. Is that
I mean, in most of the works that I've seen, n is always an integer. Usually, n is 2, usually. But I think n can be non-integer also, yes.
And the other thing is, why do you long range order in space? What was the... Like, I
Sorry?
understand order in time, but why define the time crystal, why you thinking long range order in space as well? That's not really clear.
Because it is taken, I mean, that is like the definition of time crystal, to say that it is like any robust phase, like a solids or liquids. I mean, in which there is in solids or say in ferromagnetic phase, there is long range order in space. So it is kind of done in a similar way. And there has to be some kind of an average observable, which is non-zero when we look at it. So usually it is, the definition is that this, it should be a robust phase in the sense that there is long range order in space already in usual equilibrium phases. So that part is kept, that condition is kept. In addition, there is also long range order in time. But you are true that long range order in space sometimes does not make sense. For example, say if there is not a lattice system, if there is kind of an optical lattice, optical cavity kind of system.
But is that a necessary condition?
But yeah.
If you don't have that, yeah, I mean, this is
as I said, I'm
critical or something of that kind. The long range order is
okay, I would say it is necessary all the time, because in some cases this long range is not even defined. For example, in this, the ones that I will show in the next slides, if you have an optical cavity which is not in a lattice, like several atoms together, one cannot even define what is long range. But there is a many body order, basically. Does that answer your question?
Yes, sir. You can start.
Yeah. So this is long range is more valid for a say lattice kind of system when there is a spin chain or a 2D spin lattice. Anyway, so this kind of time crystal has already been seen experimentally in say ion trap experiments with disorder, where the disorder caused localization and it stopped the heating up of the system, and or in optical cavity kind of system. And the kind of setup that I'll talk about is this kind of optical cavity, in which say there are several atoms which is coupled to some photon. And this is the Hamiltonian. A is the annihilation gradation operators of the photons, and Jz is this angular momentum operator of these atoms. And it is coupled through this Jx A plus A dagger term. And this lambda is the parameter which is changed periodically. So if say we, couple decouple between the system and the photons, what can be expected is that this decoupling can heat it up. So there is also a dissipative bath shown by this this coupling constant kappa. So any heat kind of goes out to this bath. And then this periodic behavior in lambda, it has been shown that can give rise to a discrete time crystal. So this is an open decay model in which the master equation is given by this. So Hamiltonian is the Hamiltonian I showed in the previous slide. And this dissipative operator is given here. Kappa T, I have just taken here as a general time dependent function. But at least for time independent kappa, it shows the rate of thermalization, and it has been shown that for lambda greater than some critical value of lambda c, so there is a superradiant phase transition, and above lambda c, two steady state symmetry broken steady states appear, rho ss and rho ss primes. So what this change in lambda, like this lambda is equal to 0 for half of the time and non-zero for the rest half of the time. What this periodic modulation, what it does is, it kind of takes it from this rho ss to rho ss prime between these two steady states. And it was shown that this lambda t allows oscillations between these two steady states with a period 2t. And this oscillation, it can be exactly analytically proved that this is what happens if, say, there is no detuning, that is the atom and the photon frequencies are same. So omega and omega naught are these two frequencies of the photons and the atoms. And this kappa t, if it is 0, that is, there is no dissipation, then this kind of modulation exactly takes it from one steady state to other steady state. That is a trivial thing. I mean, that is understandable. But now if we introduce some detuning between the atoms and the photons, and as well as some dissipation, even then it is seen that in some cases, in some regimes, this periodic behavior stays, showing that it is a very robust phase. So one can go to this in the, say, thermodynamic limit. One can do a semi-classical analysis in the continuum limit, in which this j at this average angular momentum operators and x and p at the position and momentum. One can solve this differential equation. And for lambda greater than lambda c, there are these two steady states that I talked about. As you can see, for large lambda, this jx becomes real and there is a positive and negative. And it can be shown that for this zero dissipation, it goes from one jx to other jx, the one steady state to other steady state. But now, even with presence of dissipation and this detuning epsilon, it was shown that different regimes emerge. That is, for very large detuning, we get a very thermal phase. That is, there is no periodicity. It is completely chaotic, shown by this block sphere diagram. So here, this is the average magnetization in this different x's, x, y, and z. And this is the epsilon is the detuning between the atoms and the photon. And it is a thermal phase. There is no order for large epsilons. If we reduce the epsilon, then they get some very nice ordering. It is still not oscillations between two states, but it is a limit cycle shown by these two circles on the block sphere. So it goes between these two circles. So it is still not a time crystal, but it is an ordering thing. And then for some other epsilon, it shows like a sextet in which there is an oscillation between, say, 6 states. Like this, it is shown in the average magnetization. And here the 3 points in the block sphere. Now there is one regime of epsilon for the wide regime in which there we get these two exact dots on the block sphere. That means it goes exactly from one steady state to the other steady state, also shown here in this average magnetization diagram. So here it is like it is showing that this, even though there is dissipation and there is detuning, this periodicity persists. And this is a discrete time crystal. So it was shown in 2018. But what is happening is that this time crystal phase, what we saw is, and which is also expected, that in a little bit more dissipation, it completely destroys this state. So if we want to make a time crystal, say even in experimentally, I would expect that there will be some dissipation, sometimes non-controlled dissipation. And so it is a crucial question how to stabilize this order in spite of some heat flow. So for that, we thought that if non-Markovian dynamics can help. So the difference is here all the results are for Markovian dynamics. So in Markovian dynamics, it is the system is weakly coupled to the environment, and usually the environment is much bigger than the system. So this is the most usually used dynamics, like in dissipation. Here, these bond marker of secular approximations are valid, which are approximations on these time scales of the system and the birth. So the main physically what happens is the system monotonically approaches the steady state. That is, if it is the bath is at temperature T, system monotonically reaches a steady state with the birth, and there is no memory in the sense that all information about the initial state is lost. It is a memoryless dynamics. But non-Markovian dynamics, here it appears if the system is strongly coupled to the environment and one or more of the bond Markov and secular approximations are not valid. And then what happens is, for some time intervals, system can even move away from the steady state. And this is associated with memory and information backflow. Because it is like moving away from the steady state towards its initial state. It is like there is a memory of its initial state. And we thought, since this time crystal order, it is something in time. So it is like the system has to have a memory that it had this order initially. So it needs to keep that order even at large times. So if this memory inside the inherent in the dynamics can help in preserving this state. So that's what we tried to see. Now again, just to show a bit more about this, what are Markovian and non-Markovian. This is done for just a simple two-level system. So say this dt is the distance from the steady state, distance between some state of the system at time t and the steady state. In the Markovian case shown by this blue line, the system monotonically approaches the steady state, that is, this distance monotonically decreases with time. But this red and black show the non-Markovian regimes in which the system can initially approach the steady state, and then it can go away for some time limit. It is like going towards its initial state, and then it can again go towards the steady state. So there is an oscillatory behavior, and this part in which it moves away from the steady state is associated with information backflow. So there is like some memory of where it started from. And this kappa t, that is the rate of dissipation, it is like, this in the Markovian case, this rate of dissipation is always positive. It can be time dependent, but it is always positive. That is, the information always flows, say, in the same direction. But in the non-Markovian case, this kappa t can be oscillated. It can be positive for some times, negative for some times. And in this negative kappa t is what gives rise to this strange non-Markovian behavior, to this information backflow. So that is what we asked, that if this negative kappa t or the information backflow can help in making DTCs more robust. So I mean, physically one can get this non-Markovian dynamics in this kind of, say, I mean, just one example is a two-level system, say, coupled to these harmonic oscillators, which is similar to what we are talking about here. And if, say, this interaction Hamiltonian is given by this BK are these annihilation creation operators of this bath, and this GK are these coupling constants, and this GK is like K is the mode frequency of this harmonic oscillator of the bath, and it can be, GK can be mode dependent, that is frequency dependent. So some for say GK sharply peaked about some small frequency band, we can get a non-Markovian dynamics. This is the Jaynes-Cummings model. And for this model, the dynamics, the model equation is like this. There is a Hamiltonian, the unitary part plus the dissipative part, similar to what we are considering here. And this kappa t is given by this form. So here the basic idea is this M gives the kind of inverse of the bath thermalization time or the energy band over which the system is interacting with the bath. And kappa naught inverse gives kind of the thermalization time. That is it is the rate of dissipation. If M is large, that is the system is coupled over a very, then D is always real, and it is like everything is fine. It is a Markovian dynamics. Kappa is always real. But complications arise if M becomes very small. That is, the system becomes strongly coupled to some modes of the bath, and then this sin H and cos H, just D becomes imaginary, and sin H and cos H are replaced by sin and cos, and then kappa T becomes oscillatory and can become negative, and we get this information backflow. So the good thing is here we can just say change M and tune M continuously from Markovian to non-Markovian limit and see how this existence of information backflow affects this time crystal phase. And this is called the damped Jens-Cummings model. So in the limit of, and here this Kmax is the maximum this kappa, possible value of kappa T. So in this Jens-Cummings is kappa T, kappa max is usually infinity, but we take it to be a finite value. And the time scale of thermalization is kappa naught inverse. So the ordering has to be persistent for times much longer than kappa naught inverse. Only then we say that it is a time crystal. And this, as I said, that it can be tuned from Markovian to non-Markovian by this changing M. So small m, when kappa naught is greater than m/2, it is non-Markovian. And for large m, it is Markovian. And m much greater than kappa naught is the time independent Markovian limit, which was shown, discussed before. So what we see is, we again go back to the Markovian case, and we see that as expected for small dissipation rate, we get a nice time crystal phase shown by these exact oscillations. But as soon as we increase the dissipation as expected, everything is lost. It just shows a time independent steady state. And in the block sphere, it is just a single point, that is, the state does not change because the dissipation wins. Now what we did was, we just introduced non-Markovianity, but kept this kappa naught, that is the thermalization time, of the same order. Now immediately we see that we get back the time crystal phase. We get these nice oscillations and these 2 points on the block sphere, which shows that non-Markovian dynamics preserves TTC, discrete time crystals, even for high rates of dissipation. And we just check whether this depends on this time parameter D, which is like gives the oscillatory time period of the non-Markovian kappa T, or in the Markovian case, it gives a time scale over which the kappa T changes. But it also does not depend. So basically, even for the same D, Markovian and non-Markovian gives very different pictures. Left is the Markovian, right is the non-Markovian. And we then changed this, we took the non-Markovian and changed this epsilon and tried to see if all these dynamical phases appear also in the non-Markovian. And what we see is, as we expect, for very large epsilon, for some epsilon, we get this thermal phase in which it is totally chaotic, shown by this here, this oscillatory random J mu, the magnetization. For small epsilon, again, we get these two exact dots on the block sphere, and there is nice oscillation. And also for other epsilons, we get this limit cycle, other patterns. So all the complexities of time crystal of these dynamical phases exist in non-Markovian. In addition, it makes it much more robust. And we also can draw the complete phase diagram, which shows the very stark difference between these two regimes. This is the x-axis is the epsilon detuning, and y-axis is the M Markovian, this bath spectral, this say the inverse of the bath correlation time. So above this dashed line, we get the Markovian phase. Below the dashed line, there is a non-Markovian phase. These two left and right are just the same thing, but for different maximum rate of dissipation, kappa max. So the qualitative behavior does not change. It remains the same. But the main thing is, as we see in the Markovian phase above the dashed line, we have zero time crystal for large dissipation. It is all steady state, time independent steady state, shown by this magenta. But as soon as we go a little bit down the non-Markovian transition, immediately we get all these dynamical phases, and also like close to the transition, the time crystal phase is most robust with epsilon, shown by this green line. So it shows this how this non-Markovianity can be so beneficial for this time crystals. And in addition, we think that this is a long time behavior. So this can even probably be used as a probe for non-Markovian dynamics at long times. And we check that maybe it is happening because this kappa T itself has a time dependence. So probably this time dependence of kappa T is causing this behavior, this robustness. So what we did was we made this kappa T still non-Markovian but not periodic, in the sense that we added some random number ft. So we can see there is this noise, but addition of the noise does not make any difference. It still showed this robustness. So the DTC order is still preserved for large dissipation, for random noise. So this is, it finishes the first part of my talk. What it shows is basically that non-Markovian dynamics is beneficial for stabilizing discrete time crystals in the presence of strong dissipation. But still questions remain, that is, if it is valid also for continuous time translational symmetry breaking. And what we still did not understand in the first case is, does more non-Markovianity mean more stabilization? And like, how do we even define more non-Markovianity? But that is the question that I will discuss in the next slides in the continuous time crystal. But before I go, any question? Anybody? Yes? Okay. If not, I will just now go to the continuous time crystals. So in the yes, yeah.
Professor, you can go ahead.
Okay. Okay, fine. Yeah. So continuous time crystals. So here what is happening is, this is called boundary of continuous time crystals. They exhibit spontaneous symmetry, breaking of continuous time translational symmetry. So what that means is Hamiltonian is time independent. But even then we get time crystals in the absence of any external periodic modulation. It happens in the form of limit cycles, which I will show in the next slides. And it also has been seen experimentally in some kind of an optical cavity setup in 2022. And here what is happening is, say again, we have this kind of, say we have these spins, S minus S plus are these angular momentum operators, by this or this polymatrices. And there is some Sx gives the unitary part. So what this S minus S plus do is they try to take it to some time independent, some steady state. But this Sx, it causes rotations. So there is always a competition between this Sx and S plus S minus. And the competition rate is given by this kappa T, that is the rate of dissipation. Again, say for say time independent kappa, it has been shown that this in the Markovian regime, continuous time crystals emerge for small dissipation. That is when omega naught, that is the frequency of this drive Sx, is large. But again, what we ask is, if this here also non-Markovian dynamics can allow the existence of continuous time crystals for large dissipation. So as we expected, here it is the Sz, that is the average magnetization along Z direction, as a function of time for large dissipation, that is omega naught is 0.3 times kappa naught. In the Markovian case, we do not have any periodicity. That is a no time crystal, but when we go to the non-Markovian, immediately we get back this time crystal phase, that is perfect oscillations. And we also checked with different omega. So this is the top, it shows this Sz, the magnetization as a function of time. So for very small omega, that is for very large dissipation, we see that it is a completely chaotic, also seen here from this is the Fourier spectrum. So each peak shows the this existence of this frequency. So as we see, for very small omega, it is a very chaotic dynamics. So there is no pattern, there is no order. And also in the block sphere, this is like a chaotic thing. As we increase omega, that is the rate of dissipation, this omega by kappa is decreasing, we get a nice periodicity like the time crystal. And even in the Fourier spectrum, we see that there is one frequency which is dominating, which shows the frequency of this time crystal. And in the limit cycle, if we increase this omega much larger, that is much larger than the dissipation, then we again get a pattern, but it is not exactly like a very simple oscillation. This we call higher order limit cycles. In the frequency spectrum, we see multiple peaks appear. And also in the block sphere, we still get this nice limit cycle behavior, but still we do not call it a time crystal phase. It is a higher order limit cycle kind of thing because there are multiple frequencies. And here it shows the different phases. There is small regime of omega, that is small regime of this dissipation divided by this drive, in which we get the time crystal phase. BTC just means here boundary time crystal or continuous time crystal. Now, we wanted to check if this is actually a phase transition is happening between this time crystal and not time crystal phase. So we wanted to check if there is some measure of phase transition. So we did this fidelity. There is quantum Fisher information. So fidelity gives the distance between two states. So for example, if say this psi1 and psi2 are two pure states, then the fidelity is just a scalar product. For mixed states, it is given by this. Fidelity is between 0 and 1. So 0 means these are orthogonal, very far away. 1 means these are overlapping. And quantum Fisher information gives like the rate of change of fidelity, so the second derivative. And it gives how fast a state is changing. So higher QFI, quantum Fisher information, is also very good for sensing protocols. And this QFI is expected to be small within a single phase, because then the state is not changing appreciably within a phase. And it shows peaks at phase transitions. That's how one can use quantum Fisher information to detect quantum phase transitions. So here what we see, this is we took the mean field limit in which we assume that the spins are not entangled, which can be expected, say, for very small interactions. And then there is QFI is given by this. So what we see here is that for large dissipation, QFI is very small. It shows that the phase does not change. Again, for very large dissipation is here, or very small dissipation, the QFI does not change. But in between, there are suddenly these peaks in QFI, which shows that there is a phase transition between this continuous time crystal and not time crystal phase. So there are several peaks, means there is some kind of a chaotic regime, and there is a non-time crystal regime, and there is a time crystal regime. So this QFI exactly shows that this phase transition is happening, and this critical point is actually moved because of this information backflow. And we also check the phase diagram. Again, we see that for Markovian case is very different from the non-Markovian case. In non-Markovian case, we get all these dynamics, all these dynamical phases, and we get this time crystal for very large dissipation. But for the Markovian case, above this line, solid line, we get time crystal only for very small dissipation. But we had the question that how does if more non-Markovianity is better? So we used some parameter measure of non-Markovianity, which is given by this n, which is like integral of this f. F is non-zero only if kappa t is negative. So whenever kappa, the information backflow is happening, f becomes non-zero and we get n. So it gives kind of a how strong non-Markovian it is. What it shows is very little non-Markovianity is not good, very large non-Markovianity is not good, but there is an intermediate sweet regime in which we get this time crystal phase. So it kind of shows that, what kind of information backflow, little bit information backflow is good, but not too much. And this y-axis FFT peak ratio, it is just the ratio between these Fourier peaks. So FFT is large means only one Fourier mode is the dominant one, which is the time crystal phase. But FFT small means the several Fourier peaks are of the similar magnitudes. So these are not patterns, but this is large FFT means it is a time crystal phase. And we are also thinking of next checking the eigenvalues. So this can be this time crystal actually emerges when the eigenvalue of this Liouvillean, the real values are negative, and this we get imaginary eigenvalues even for almost zero real negative eigenvalues. So here it is the non-time crystal phase shown in this Liouvillean spectrum. So what we see is that all the real eigenvalues are negative. That means it is a decay, and there are no imaginary for large real. This is the time crystal phase. This is all in the Markovian regime, which was done before. So here what is happening is the imaginary eigenvalue, even for zero real eigenvalue, this is what gives rise to the time crystals. This is doing this is a bit more complicated in case of this Markovian regime. So we are now working on that. In any case, this brings me to the conclusion. So the main message of my talk is this non-Markovian dynamics is highly beneficial for stabilizing discrete and continuous time crystals in the presence of strong dissipation. And an intermediate regime of non-Markovianity parameter n stabilizes these continuous time crystals. So too much non-Markovianity or too little are not good. Intermediate is good. And this Markovian and non-Markovian regimes look very different in the phase diagram, both for the continuous as well as the discrete. And this continuous time crystal phase transition is also seen by this quantum Fisher information. And the idea is probably they can be also used to differentiate between this Markovian and non-Markovian dynamics at long times. So thank you.
I request you please come here. Yeah. Communication. Sure. Come here.
Hello, Victor.
Yes.
Can you hear me?
Yes.
So I have a small question. Like when you define this time crystal, so what will be the analog of Brillouin zone and the other things which we have in space crystal?
So that is like in the Fluke method, there is I cannot think of any analog like that. So in the sense that one can do this Fluke method in the even in the time crystal case, because it is a periodic in time. So other than that, I do not remember any work that talks about this. But in any case, yeah, I just can think of this kind of Fluke method to study these things that might be closest to it. But other than that, I don't think that is any kind of analog is still now known.
So yeah, hi Victor. Hi. So
Hi,
one
hi.
question, Victor, is the way you are introducing non-Markovianity is still keeping the equation local in time, right?
No. Locally, it is
Because
not
your kappa
exactly
is
because
still, if I look at the master equation, it still just have a kappa of t. I think that is how you're introducing non-Markovianity, right?
true, but actually since it is a cos omega t sine omega t.
Yeah, exactly. Hyperbolic becomes oscillatory now. That's the
Exactly.
main difference, right? Yeah. So
Okay.
yeah. So the point is that so you can still think of a Liouvillean.
Yes.
A Liouvillean, and you mentioned that for continuous time crystal in the thermodynamic limit, you expect emergence of a eigenvalue which has a purely imaginary component, and
Yes.
that's really necessary and sufficient condition to have that. What about for the discrete time crystal? Like, is there any like how do I sort of
Okay.
I can
So
still
in
talk
the
about a
discrete,
Liouvillean there as well, right?
yes. So in the discrete time crystal, the Hamiltonian is time dependent, so the Liouvillean is time dependent. There one cannot exactly look at the eigenvalues of Liouvillean just like by that.
Okay.
But one needs to look at this eigenvalues of this total unitary operator, this time
That's right.
ordered unitary operator. So yes, I mean there I would expect that it would have both this imaginary and real components as well in this time crystal.
That's right. That's right. Yeah. So, but there are also, a question that still really remains unanswered. That there are other ways to introduce non-Markovianity, right? I mean, for example, like you can do something like a pseudo mode, or like a reaction coordinate, or literally putting a memory kernel into the evolution. So I think those things are still not really
Yes, yes,
explained, if I
yes,
understand well. I see.
I agree.
Yeah. Thanks.
But the main idea is whatever non-Markovianity is introduced, the main thing is there is information backflow.
Yeah,
So
that's
I would expect that it should hold in all cases.
right.
So if not, let's thank the speaker once again.
Yeah, thank you, Victor.
Thank you. Okay. Time stop.
And we expect to have you in person very soon here. Okay, thank you so much. Thank you.
Thank you. Okay. Bye.
Okay, so yeah, so we will now have a quick break of 10 minutes. But there will be an in-person talk. So then that will be very nice. And after the lunch session, there will be also 4 talks. So we will come back at 12:37. Thank you so much.
Recording
Recording for unlimited access. এই স্টকটা হয়ে যায় কেন এই স্টকটা পড়াশোনা করা যাবে এটা তো আমাদের কাটতে হবে এটা দিতে হবে না রেকর্ডিং বন্ধ হলে আমি আসলে যেটা করি যখন লিভ করে দিই আলটিমেটলি ফাইলটা সেভের জায়গায় চলে আসবে আমাকে রিকানেক্ট করতে হবে সেটা দেখেন কেটে দিলে একেবারে রেকর্ডিংও কেটে টেটে আমি সেটাই বলছি 10 মিনিট যদি ঘুরে গেল আমি রেকর্ডিংটা পজ করতে হবে না আরেকটা সমস্যা হচ্ছে অবশ্যই একটা টক না আরেকটা অসুবিধা আমি সেটা বলছি আরেকটা টক হয়ে গেলে তাহলে একবারেই করে ঠিক আছে সেটা কারণ এই 5 মিনিটের হার্ড ডিস্কটা যেটা আছে বেশি বেসিক নোটে তো 56 জিবি হয় তারপরে না আমি রেকর্ডিং এর কথা বলছি রেকর্ডটা কত ঘন্টা রেকর্ডিং যদি হয় 5 জিবি ঠিক আছে 5 জিবি অবশ্যই
यहाँ पे होगा सर
আপনি এখান থেকে তাহলে পেন ড্রাইভে আসে তাহলে এটা রেসপন্ড করবেন, তাহলে এটা খুলে দিচ্ছি আমি, মানে পেন ড্রাইভে তাহলে এখানে ডাইরেক্ট এটা তো এটা এইচডিএমআই, এটাই টাচ সেন্সরটাকে করার জন্য এইটা নিতে হবে actually। আমার ল্যাপটপ থেকে আমার ল্যাপটপে তো এইটা লাগাতে হবে, আদারওয়াইজ আমি অমিত থেকে পাঠিয়ে দেবো। স্যার এটা আমি খুলে দিচ্ছি, এটা তো এইখানে চলছে, অসুবিধা নেই। ঠিক আছে, আপনার এইটা লাগবে তো, কানেক্টরটা লাগবে? হ্যাঁ করতে থাকবো, না না আমি ওটা করি না, আমি এটাকে মেলে পাঠাচ্ছি, ওখানে ডাউনলোড করবো, আমি দুবার করতে পারছি। তোমার ইয়েতে পালক্কাডের আইডি রিকর্ডিং, রাইট? না জুমে শেয়ার তো করিনি আমরা, জুমে শেয়ারটা করতে হবে, রাইট? এই যে তো এই জুমটা বন্ধ হয়ে গেল আবার।